Hello, in this video we are going to review the Simplex method for linear programming in SAS. I have the code here on the right hand side that gives us the Simplex method in SAS. That being call LP solve parentheses RC comma obj value X dual reduce cost CAB CNTL row sense range L and U. But as you can see inside of this code, we have a whole bunch of parts and pieces to this code. The first, that RC value, that's a return code, and the only thing that matters with that is whether or not it could solve the linear program. For the most part, we're not going to have to worry about that in this class. The obj value option, this gives the optimal or final objective value, and that's the number that we typically want when solving the linear program. X is the solution or the primal solution in a column vector of length n. That is the point of the optimal solution, and as such we want that. We want that as an answer. The dual returns the dual solution of the matrix in a row vector of length m. That is the corresponding dual of the matrix, so then that way we don't have to rewrite it in order to solve it, as it already solves it for us. The only problem with that, though, is it does not give us the optimal solution for that. Do bear that in mind. But at the very least, it gives us the point, especially if it's a more complex type of linear program. It might be useful. Reduce cost is the reduced cost of the column vector. That's typically not needed. C is the vector of dimension n. That's the objective function coefficients. So you would write the objective function as coefficients in that vector. A is an m by n matrix of the coefficients of the inequalities or constraints. B is the vector of dimension m on the right hand side values of the inequalities or constraints. CNTL is a vector with various properties, and there's a whole range of them that you could find on the SAS website. The only one, though, that we're going to worry about for this class is the first value of it, which determines the type of linear program that we have. So we're going to refer to CNTL as +1 if it's a minimization problem, or -1 if it is a maximization problem. The row sense value, well, variable, I should call it, not a value per se. The row sense variable is a row vector of dimension m that specifies the type of inequalities or constraints that we're using based on those inequalities. So E is used for an equal constraint, L is used for less than or equal to, G is used for greater than or equal to, and R is a range. But typically R is not used, or not as predominantly used as the other types. The range variable, that is the specific range of the constraints. Again, that is not a value that's typically given. L is a column vector of dimension n for the lower bound of the variables. This is assumed to be 0 if left blank. And U is a column vector of the dimension n for the upper bound of the variables. Again, if it's left blank, it's typically, well, I shouldn't say typically. If it is left blank, it is given a value of infinity. And you could check out SAS to see the website to see about more examples involving that. But let's say we want to solve this linear program that I have on here. We want to maximize the objective function 5x minus 6y, where we have x minus 2y is less than or equal to 4, and x plus y is greater than -2. X is greater than or equal to 0, but y is less than or equal to 0. And I have the graph of this solution, and let me put that into Firefox over into Firefox over here on the left, just so we could see it. Once it decides to load, of course. Well, we could see I graphed it on here. We have a whole bunch of different inequalities graphed. And we could see inside of this area down here, because we want x to be greater than or equal to 0, but y less than or equal to 0, we have this triangle right here where we can see these 3 points. And those 3 points are labeled down here. A value of, for x and y both being 0, the objective function is of course 0. If we have an x of 4 and a y of 0, we could see the objective function takes the value of 20. And if we have an x value of 0, a y value of negative 2, that gives us a value of 12. Naturally, since we want to maximize this, that maximization point is at this point right here, which is at that point 4, 0, and the objective function gives a value of 20. Now to put this into SAS, I have typed that already over here on the left. We always start with proc IML. That's just the procedure that LP solve is in. You do need that inside of the program. That the lower bound I called for this because we want x to be greater than or equal to 0, but we don't have that constraint for y. Right? So the lower bound, well, we want y to be less than or equal to 0, but that's besides the point. The lower bound then for x, since we want it to be greater than or equal to 0, the smallest it could be then is 0, so 0 goes there. And the upper bound of that for the x variable, the value that we could use for that, since it naturally defaults to infinity, to use that default value, we're just going to put a dot. And then for the y variable, we want that to be less than or equal to 0. Right? So 0 now is our upper bound for the y, and we don't have a lower bound for y, since we want y to be less than 0. So we just have a less than or equal to 0, I should say. So we just put a dot in that for the lower bound. And notice we don't have any commas or anything. It's just a space to denote those two variables. And based upon this, our objective function of 5x minus 6y, we just take the coefficients for the coefficient vector, so that being 5 and negative 6. Oh, and all these lines have a semicolon at the end of it, due to the SAS programming language. CNTL, so that's the bunch of a vector with a whole bunch of numbers. The only one that we care about for this is to denote that this is a maximization problem. So negative 1 goes in for that. If we left it blank, as in didn't provide any numbers for this, it would count it as a minimization problem. So do bear that into mind. Next is our matrix. Where we write each row out and then put a comma to go down to the next row. So here we have the constraints, the first two ones here, since we already dealt with the last two. These first two, x minus 2y, we write that as 1 and negative 2 due to the coefficients of that. And then for x plus y, we use 1 and 1. And then again, we have those surrounded by that curly parenthesis bracket. And then the solution vector B is these two last values, so 4 and negative 2, separated by a comma. And then due to this being a less than or equal to and a greater than symbol, we have L and we have G for the two constraints for that value of LEG or row sense in the document I was just reading. So now that we have all those parts, we could put them into our code. So we call lpsolve of RC obj value would be our variable for that, for the objective function. X is our solution, dual, since we're going to look at that in a moment. We'll do cost C, A, B, C, N, T, L, L, E, G. And if you remember from the code I had all the way up here, we had the range. I'm skipping the range on this, so I just have comma and then another comma right after it to denote no usage of that range variable. And then the lower bound and the upper bound, which we specified. And then in order to print out these values, we use print obj value for that value of the objective function at the optimal solution, x, and then we rename them. You don't technically have to do that, but because the values that it would give in SAS differ than the values we used in the function down here, that's why I specified it. You technically don't have to, but I specified the row names as x and y, just so it matches the problem. And then dual gives us that dual solution. And if we run this, and we give it a moment to actually run, it gives us that the optimal solution of 20 at the point 40, which is exactly what we saw on here for the graphical solution of it. It also gives the dual solution of 50. And the dual of this linear program that we have, I wrote down here, as the minimum. And if you want to see how to do this, this is in section 9.4 from our textbook. But it's the minimum of negative 4x1 minus 2y1. And then we have negative x1 plus y1 is greater than or equal to 5. 2x1 plus y1 is greater than or equal to negative 6. Then x is less than or equal to 0. And y is greater than or equal to 0. The graph of that is this one. We wanted the values then within a range on here, and we could see that the solution, which it provided for us, not there, here, as 50, that being 50, which I put down here. And that gave us a minimization of negative 10, which is indeed the smallest value that we have on there. So that is indeed where all of those numbers came from for that. Thank you.